Hello, everyone. We'll get started so that we don't get delayed. I am Serena Pop, and I'm delighted to be here today with you. I'm the moderator of this session, which will talk about simplifying data-driven science with user-friendly platforms and gateways. And our first speaker is Tamas Kis, that will talk about the Pythia eCenter Science. Thank you.
Okay, thank you very much for the introduction. So I would like to just give a quick overview of a project and what kind of science gateway we have developed in that particular project and how it supports data-intensive science. So, no? Okay. Good. So just a quick introduction to the Pythia project. Pythia is a 4-year European-funded project which started back in 2021, and we are about to finish the project in March 2025. So we are towards the end of the project. I presented, I think, Pythia a few years ago in EGI, but in a very early stages. So I thought that now this is the time when I can present practically very close to the final results, although we have 6 months still left from the project. Pythia stands for Plasmasphere, Ionosphere, and Thermosphere Integrated Research Environment. I will have one more slide which explains what it is, but practically, if you are not a domain scientist, this is the kind of very close surroundings of the Earth, anything between the Earth and the Sun. That is my understanding, but I'm a computer scientist, so I'm not necessarily understand it fully. And as it is funded by the European Commission, we are designed to integrate observing facilities, data collections, data processing tools, and prediction models in order to provide better science and a more integrated set of facilities for the community. So these are the scientific challenges of Pythia. I will not go into the details because, as I said, I understand very little about these, but there are quite a few, about 30 partner institutions from Europe who are all researching in this particular area and who have their own data, they have their own facilities, they have their own prediction algorithms. And the idea behind the Pythia eScience Center, which we have developed, is to create a single entry point for all of this data. So what is this eScience Center? And then I'm going to introduce you to the functionalities and how we have designed and implemented this. So this is practically a web portal, okay? It's a web portal which provides a single entry point to what in Pythia called data collections. Now, this word data collection may be used in a kind of non-regular way. So especially if you are a computer scientist, then you believe that a data collection is a collection of data, which is not the case necessarily in this particular case. So data collections can be data sets, which you would associate with. But this can also be, for example, a model, a prediction model. And in this case, they call data collection an executable application, okay? So an executable application is an executable program which you run on demand, that is also a data collection. So these are also registered as data collections. And we have other things like catalogs, which are kind of time-stamped data, and workflows where we combine multiple prediction algorithms in order to get some kind of results. All of this is based on a standardized metadata and ontology, and I'm going to explain it a little bit in the next slide. The idea is obviously to provide seamless integration. If you navigate to that particular web page, then you can see the Pythia eScience Center live. Thanks God I did not plan a live demonstration because that would have been a complete disaster. It's not going to be a live demonstration. So this is the Pythia ontology and metadata structure. It is a very ugly XML-based standard, which is standardized by ISO, and the community kind of insisted using this because of the standardization. So when we came to the project, we didn't have a choice. We've been told that you must use this particular XML standard. So we needed to live around this, and you will see that we implemented various tools to make the life of the community relatively easier. And this is a 12 set of XML files which need to be provided about every single data collection. So when a data collection is so-called registered, at the end you see number 12 is the data collection itself, but each step you describe various aspects, starting from the organization who owns this data collection, to the individual, to the project which created this. This is up to 12 steps, not always 12, so sometimes some of these can be neglected. And in each step, you also use a domain ontology. So this domain ontology was originally developed in a previous EU-funded project and was reworked for Pythia again by the community. And there are certain keywords which you can use during the registration. So this ontology is practically defining these particular keywords. So that is the very ugly structure which you can see on the right-hand side, quite complicated. But again, we needed to live with this, and we needed to find our best in order to provide the community. So you will see that we implemented a few tools which kind of frees them up from understanding at least the XML structure. So this is how the eScience Center looks like when you go to this. As I said, I was really hesitating with a live demo, but I decided I will include slides. And another thing which this community insisted on, that they wanted everything open. So everything open means is that no registration, no user identification, anybody in the world can go to the Pythia eScience Center and access all the data and do whatever they want with it. And they wanted this, and run the models as well. And they wanted this very specifically. So they said, no, we don't want any kind of control. We want fully open science, and open for us means that, yeah, it's open. You can just go there and you can explore. So these kind of pages are open for everyone, and there are other pages where you browse, for example, the space physics ontology. But then there is one section in the Science Center which is not open, and obviously this is for very, very good reasons, and this is the registration page. So if you would like to register a new data collection, if you would like to offer something for the community, then you need to tell who you are and where you belong to. So that's, you cannot publish any kind of information in the Science Center. That is very much controlled. So in this case, you see I logged in and my institution is the University of Westminster. And then there are certain data collections which I can manage in this setting. So one of the main objectives of the eScience Center is to find things, okay, to search for things. So we implemented various ways of searching for data. The simplest way of searching for data is browsing. So this is a simple browse where you have various categories, and you just click on the category like activity indicator, sensor measurement, and so on. And then by clicking on that, you can see all the data collections which are listed, and then you can go and you can find it. It is very simple, so you can just click on the relevant data collection per category. Now, a little bit more sophisticated way of finding a data collection. Obviously, at the moment, we have about 70, 80 data collections. So even with the browse, you have a good chance to find what you are looking for. But we also implemented various searches. So we have a search based on various keywords. So you just simply type in the keyword, and then you find the data collection, which anywhere in the XML description refers to that particular keyword. So this search is going through the XML tree, the entire XML tree, and then finds the data collection with that simple keyword. And then all data collections for that keyword are listed. And then the final one, and this is the most kind of scientific or sophisticated one, is to find a data collection using the ontology. So if you are a domain scientist, you well understand what you are looking for. So you just tick boxes of the ontology. You can search for what is called feature of interest, so Earth, heliosphere, and so on, computation type or instrument type which created that data, or what is observed, so the observed properties. You can combine all of these and you can find what you are, what you are interested in. An interesting thing regarding the implementation, that this most sophisticated search was implemented first, because they wanted us, we would like to search based on the ontology. And when we implemented it, they said, it's too complicated. It's okay for us, But for a PhD student, it may be too complicated. Let's implement something more simple. So many people like this in the community and use this, and others said, no, I will never use it because it's just too scientific. So that's why we implemented the other search functionalities. And then obviously you just press search and you search for the data collections. Now, once you found the data collection, then you would like to interact with it. So that means that you go to a page, something like this, where you can learn a little bit more about. If I scroll down on this page in a live demo, then you can see that there's a lot of information based on the XML registration content. So all of this data is obviously coming dynamically. So that was the other thing which was very interesting to talk with the community, that they said, okay, so my data is not correct. And I said, that's interesting because you put it into the XML file. So in order to change anything, you need to go to the XML documents and you need to change the XML documents. And obviously, this is dynamically displaying it. And then you can click on a link where you can access the various data collections. We have two main ways of accessing the data collection, from a very simple registration to a little bit more complex one. So for example, in this particular example, I just clicked on a link and I went to the remote site. So this is where the data is stored. It is not stored centrally. It is stored by the institutions within the community, and they provide access to the data. So in this particular case, I'm actually going outside the science center, and all the data which I'm looking for is chronologically listed there, and they can download it and they can access it and they can do whatever they want with this. Another way of accessing the data, and this is a little bit more sophisticated, is then the model is executed from the science center dynamically. So this means that you found the data in one of the ways which I've explained before. So you find the data collection or computational model in this particular case, and now you would like to execute it. And in this case, you can go to an API. The API is described by the owner of the data. And from the API specification, we automatically generate a GUI. So this is a Swagger UI interface, which we customized in order to look like a Pythia user interface. And then you can execute the model by clicking on the appropriate link. So this is how the customized Swagger UI interface looks like. We have the various functionalities of the API endpoints. The users can select any of these, and then they can provide obviously the parameters, and then the execution starts. The execution either runs on EGI, so we deployed these models on EGI resources. Some of them, but some of them are also deployed remotely by the community because they don't want to move their models anywhere else. So in that particular case, it is running, but in both cases it's running remotely, but it is running on the original site. And then obviously, once you run the model, then you can observe the results and you can see the actual outcome of the model. We also implemented a couple of workflows. Again, this is a starting community, relatively less experienced. They were not 100% sure whether they have workflows, they don't have workflows. So we decided not to include at this stage a workflow engine. So we did not use a kind of predefined workflow engine. That would have been a kind of overkill in this particular case. They are still thinking about how many workflows they have. So we have a couple of workflows at the moment implemented. In case the workflow, it works a very similar way. You find the workflow, you learn about it, and then there is some additional information how the workflow looks like. So this is, for example, uploaded as workflow additional information, which explains the user what kind of data collections are combined in this particular workflow. And then the execution interface is exactly the same as in the previous case. So this is a modified Swagger UI. And then once you executed the workflow, then you can visualize the outcomes of the workflow in the science center. Again, they are struggling at the moment to find new workflows. We are in discussions that we are going to implement probably 3 or 4 additional workflows before the end of the project. So I already mentioned that in case of managing resources, you need to register as a user. And we implemented this because EGI is a partner in the project besides us. So we implemented it using certain EGI services, which means that we are using EGI check-in and Perun for authentication and authorization. It was a little bit of a challenge because during implementation, it turned out that Perun by default did not support all the functionalities which we needed. It was, I'm not saying complicated, but this was a relatively complex setup. So when a user registers, a user belongs to an institution, and only resources which are belonging to that institution can be managed by a particular user. These are institutions inside the Pythia VO. So these are a kind of additional, it's not an EGI kind of thing. Pythia itself is a virtual organization in EGI, and then inside the VO we have what we call various institutions. So only those people who are belonging to that particular institution can manage the XML files. So I said that we've been struggling with the inherited XML structure, which was slightly modified during the project, but they did not want to change from the XML structure because the ISO standard is still using XML, although the ISO standard somewhere in the roadmap has the idea of transferring to YAML, but at the moment it doesn't exist. So we needed to live with the XML file. And in order to support the community with the registration process, we implemented a simple wizard. It was not that simple because we have 12 different XML files. And yeah, so it was a relatively complicated stuff to do. So this is the wizard interface, which you see. There are some fields which the user still need to complete by typing information, for example, the name of the data collection. But there are some others where they can now just select from drop-down boxes. And these drop-down boxes are typically coming from the ontology. So if the ontology changes, then the drop-down box will change as well, because we are following the changes in the ontology. And some information we can generate automatically. So IDs and stuff like that, they don't have to bother with anymore. They did like 90% of the registration before we implemented the wizard. So they unfortunately went through the hard stuff. But now the new data collections doesn't need to be registered in that way. And then once the registration is over, they just click on a button and then a validation takes over. So we check the XML syntax, we check the XML schema, we check the ontology, and we check the dependency between the various XML files, whether the user is keeping that or not. And I think I'm getting to the final slides now. So this is how it is deployed. As I said, we are working with EGI. So most of it is deployed on EGI resources. We're using certain EGI services like Check-in, Perun, Gigas for ticketing, and Argo for monitoring. Some of the data collections are, as I said, deployed outside. So these are community services which are not on EGI resources, but the eScience Center and some of the data collections are actually deployed on EGI. So that is it's on IN2P3 in France, who is our resource provider. These are a few numbers about the Science Center. So currently we have 61 data collections, 2 workflows, and 2 so-called catalogs. This means altogether 834 XML files. So that's a kind of scary large number. There are some which are just being registered, that not all of them are used, but this is a very large number of XML files, and I copied the wrong version of this. So the number of, because I am pretty sure that I updated these. So the number of users is about 35, I think, but be warned that the user means admins. So these are admins from the institutions who are registering the resources. And we have about 22 registered institutions. Again, sorry that these are missing from this slide. So thank you for your attention.
Thank you very much, Tamás. Perfectly in time. We have time for a short question.
Thank you for your presentation. So I saw the authorization was done by some parent, right?
Yeah.
So how would that be, I don't know, how would it be difficult to kind of make the EGI environment infrastructure-wise, like AI? I don't know, like if there was a discussion or something political. Yeah, maybe you could elaborate.
Yeah. So yeah, there was a discussion. I'm not saying political. There was a discussion that what kind of authorization service to use. And EGI is a project partner in this project. So obviously, yeah, they came up with this suggestion that we are using Perun. It was not straightforward, but I think the major issue was that we wanted things which Perun did not support. So they needed to develop it on the fly as we progress with the implementation. So altogether, it took a lot of time. It took like 6 to 9 months in the project to implement this. But most of the time was us coming up with the requirement and then waiting for EGI to implement the service. And then obviously to troubleshoot it, because this was a new development, so was not tried by another community before. So it took some time. I think in the end, I would say it was worth it. Yeah, it was a little bit, there are always problems in a project, and you always try to work together. But I think it turned out quite well. The other option is that we had a system which we implemented based on OpenID Connect, which was already, probably that would have been faster for us. But I think from sustainability point of view, this is a better solution.
Thank you again, Tamás. We will now welcome Stefano Chiappini, who will be talking about the virtual data center.
Thank you, Sorina, and good afternoon. I am Stefano Chiappini from the Italian National Institute of Geophysics and Volcanology, and today I will talk about our experience in building a platform to give data scientists flexible and integrated environment to deploy online services for data processing and sharing. This presentation should have been presented by me and my colleague Stefano Cacciaguerra, but unfortunately he could not attend this workshop. So the reason behind this work lies in the need of modern scientists to have always more collaboration and more interaction on a wide geographical basis. And then share larger and larger amounts of data due to complexity, increasing complexity of modern research. Moreover, technological advances and increasing in computing power allow for always more sophisticated data analysis system and complex scientific simulations. So we, as a real example, we took the case of EMSO. EMSO is a European Research Infrastructure Consortium focused on marine sciences. Italy is the coordinator country, and my institute, INGV, is the representing entity. So we implemented NEREIDE. What is NEREIDE? NEREIDE is the acronym of New Research Infrastructure Data Center for EMSO, and is an infrastructure, an ICT infrastructure designed for scientific data archiving and processing, and to develop advanced services to promote multidisciplinarity research in multidisciplinary research in the field of deep marine environment. So this gives just an idea of the size of NEREIDE and an overview of the whole process from the very beginning, the budget allocation, through the whole steps, data design, technical specification, the very boring legal and bidding part, which was a nightmare, up to the very end, installation, configuration, and entry into production. The software architecture of NEREIDE is based on OpenStack for the cloud component, Chef for the storage component. Workflow automation is achieved by means of the tools developed by Canonical, MAS, Metal as a Service, I'm fighting with and Juju. Okay, I think in this room, OpenStack and Chef are very well known, so I won't say more about this. So now we are at the point, the concept of virtual data center, which is the core of NEREIDE. Virtual data center is a managed environment designed to allow more flexibility in both resource management and development processes by the data scientists. This is achieved by putting a custom gateway in front of the virtual data center, And this gives the capability to manage and configure, in addition to virtual machines and network, which is a capability of OpenStack, also firewall rules, virtual private networks, and routing configurations. Just a few words about the administrative levels. We have the data scientists are the manager inside the virtual data center, while infrastructure administrators keep control over the infrastructure as a whole and the physical resources. Okay, this is a schema of just what I just said. So the top levels are the top administrator deal with architecture design and the creation of virtual data center. Then in the middle level, where there are the data scientists who administer the virtual data center and develop or deploy the services inside. And then the last level, the end users who can access the services deployed inside the virtual data center. This is a diagram of a virtual data center. There is, which is made by a tenant, which is the OpenStack object project. So it's a tenant and is the container of the virtual machines and eventually other private networks. These resources are connected to an external network which has a role-based access control policies defined on it. This network is then connected to the custom gateway and the gateway to the outer network. All the gateways are deployed inside, let's say, an administrative tenant. Here is called T0, and this is under the control of the infrastructure administrator, while the tenant is under the control of the data scientists. Okay, the custom gateway is basically a virtual machine with the Endian Firewall Community Edition distribution installed on it. It is configured with a single public IP address, while the internal interface and all the BAC network is configured with private IP. And inside the virtual machines, there are the deployed services. Here, there are some examples. So what is Endian Firewall Gateway? Is Endian Firewall Community Edition is basically an open source Linux distribution optimized to work as a router/firewall with several other capabilities, such as antivirus capabilities, intrusion detection system, virtual private network, and many other. And also has an interesting dashboard, graphical user interface to manage and to enable and configure all the services. While this can be accessed by the data scientists, while the ownership of the root user of the operating system is still on the hands of the infrastructure administrators. So I talked about several services, but the mostly used are the firewall services, obviously, which are, okay, source NAT is basic because VMs need to access internet. But the add-on, if we compare to the OpenStack object router, is, for example, port forwarding, which allows to make accessible the services inside the virtual data center from internet. This is typically used for user access. Virtual private network to securely access all the resources inside the virtual data center. And this is typically used by developers. And this is done by an OpenVPN server integrated inside the Endian Firewall community, which can be used from both client-to-site connection using OpenVPN clients, but also site-to-site connection through IPsec tunnels. So having in mind the goal of a more efficient and a faster management, we are integrating into virtual data center infrastructure as code to allow to provision services through version controlled scripts. This because we want to reduce manual intervention and thus increasing stability, reliability, and also reproducibility. And if we have scripts to develop, provision the services, they also ready to use and they also rapidly provision. Can be rapidly provisioned. So the idea is to make a framework to allow cloud automation and orchestration possible. So to conclude, virtual data center represents a sort of evolution in the concept of virtualization, not only restricted to virtual machines, but also to other data center infrastructures, such as networking, firewalling. And so this more flexibility, the keyword is more flexibility. With infrastructure as code, we we allow rapidly deployable services. So the keyword is more speed. So by facilitating, trying to eliminate these complexities, the virtual data center try to accelerate the achievement of open science goals. Last, virtual data center can be integrated with other federated data infrastructure to enhance the capabilities and resource sharing. Okay, thank you. Was in time?
Thank you very much. Perfect. 8 minutes, 30 seconds. So we do have time for questions, 1 or 2 questions. Do you have some?
Everybody's scared.
So one question for me is that you know, sometimes when you want to make it easier for end users, right, to do science, you know, sometimes when you support them, depending on the background of the end user, sometimes they even struggle if you ask them to create a public or a SSH key pair, for example, to access services or VMs. So I see it's a very nice setup for the security of the virtual data center, but then it's adding also complexity, in my opinion, to how the end user is going to access their resources. So my question is, how are you dealing with that?
Okay, thank you for the question. They disappeared because I can explain better. If you're talking about end users, actually end users access only the services already deployed. For example, an AirDAP server, a Jupyter Hub, something like this, which should be at their, you know, in their capabilities. What maybe you are referring to the virtual data center developers or data scientists. Okay, they are developers, so in principle, we assume that they know what they are doing. If they are trying to set up a service or more services, I think these are the basic to manage SSH keys or firewall routes. Or okay, for example, they need to open a port, they need to open a special port, or they need to configure a reverse proxy, something like this. But with infrastructure as code, for example, we're trying to simplify this one. So you need a reverse proxy. Okay, we have a script already done. You need to have a virtual machine ready for Docker containers. We have a script to do. So this is simplification. Okay, then everybody has to have some knowledge, obviously.
Thank you. Do we have a second question? No. Thank you very much. Then Stefano. And we now welcome Gabriel Pelouze, who will talk about collaborative research with notebooks as a service, as a VRE.
Hi, everyone. So I will present you the notebook as a VRE platform, NaVRE for short. This is a joint development effort between LifeWatch Eric and the University of Amsterdam. So the context in which we are is supporting data-centric research activities. And we all know those activities do not exist in a vacuum. They are connected to different aspects. Usually you start with hypothesis and discover data, and this needs to be connected to external repositories. Then designing your experiment, you turn this into code, and this has to be executed somewhere. Most of the time, your laptop is not enough, so that has to involve remote infrastructure. And then, of course, central actually throughout all the steps, you have a strong community collaboration aspect. So in this context, we look at virtual research environments. And the options for supporting those activities are, you can support this with computational notebooks on the one hand, and virtual research environments on the other hand. Now, if we compare them, we see they have very different strengths. Computational notebooks, they are widely used by the research community. They're very interactive, very easy to use. You can document, visualize your results directly alongside the code. Essentially, it's a very powerful tool for iterative development and tweaking of code models, etc. But they lack key aspects that are usually found in a virtual research environment. Collaboration, as in sharing assets within a community, not just working together. Verification of those assets, and then connecting to some remote infrastructure, especially for scaling up models. Of course, some of those aspects are supported with notebooks. You can submit things to remote infrastructure and so on, but you will still be bound by the machine on which the notebook is running. And so we have, on the one hand, this notebook that's nice for iterative development. On the other hand, this virtual research environment that's better for sharing more mature model workflows and so on. But what we observe is that in virtual research environments, the entry, the technical barrier to start using a VRE is quite strong. And so the idea behind this NavVRE platform is to combine the strength of both. How this is done is by supporting all these aspects of the experiment life cycle with a set of extra features that are added to the Jupyter Lab environment. The way it works is that we have extensions for Jupyter Lab. Some of them are connected to external services, and those are all available through a marketplace where they can then be put together and customized into virtual labs. So this part now is entering a bit more as it's not directly a live demonstration, but you have a video on the side. So those virtual labs are built on top of a platform as a service that itself is deployed on top of OpenStack and Kubernetes. And so in this platform as a service, we can dynamically create virtual labs, which are customized environment for a given research community. And in these virtual labs, we are going to have virtual lab developers, which can be roles very close to researchers, because all this work is done in the Jupyter Lab environment. Concretely, how does that work? In Jupyter Lab, we allow users to go very easily from a notebook, which the users are familiar with, as we said, to a fully automated workflow that runs in the cloud. So you start with editing, prototyping your model in the notebook. And once you are happy with the behavior, you can select a cell and containerize it as a reusable element. The way this works is that we identify the input and output variables of those cells, as well as parameters, and we can generate a description of this interface. I have a video here. So you see we are selecting, well, first making changes to this notebook. And then once you select a cell, you have a description of the input and output. And then you can convert this cell with just a few clicks into a Docker container. This Docker container is added to a local repository, a local catalog, and is available within the virtual research environment as building blocks for creating workflows. So you go to the next step, which is composing a workflow. You have those building blocks available, and you can assemble them into a new workflow. Now, workflows are a very common thing, but we have a feature that I think is quite, we don't see that in many workflow composers, which is the ability to split the workload into different containers. So for instance, if the users want to process a very large list of files, and maybe they don't have big technical knowledge on writing themselves optimized and parallelized code, they can use the splitting and merging functionality in this workflow editor to essentially say, let's split the workload here, and then we generate the splitting and the merging when we execute the workflow later on. So that allows to take advantage of the more resources that you have when you run a workflow in the cloud. So once you have composed your workflow, you can submit it to a workflow engine. In our case, we use Argo running on Kubernetes. And as you can see here on this example, this is an example with a splitter. And you see, although the user never did any code to handle the parallelization, we create several instances that will process the files in parallel. Now, of course, how much you can split this depends on the availability of the resources in the cluster. But the nice thing, if we are on an open stack on a Kubernetes machine, is that it's very easy to dynamically add resources if user needs to run a large data processing workflow. So we use this to support several use cases in the ecology and ecosystem field. We have currently several virtual labs that use Naviary, some LiDAR analysis of vegetations. Maybe I will not describe them all, but we have several use cases. And I want to also show the last slide, that this is a continuous development effort. So we are constantly adding new features. This is our current spotlight, let's say. We are now supporting containerization of R code in addition to Python. I haven't mentioned that, but mostly we are targeting Python, and now we also support equally R. We're also looking into supporting other notebook-like environments, such as RStudio, which is very popular in the ecology community, adding dynamic visualization in those workflows, and enhancing the fairness of the notebooks, the workflow components, and the workflows themselves by using FDO. And that was it, I think.
Thank you very much, Gabriel. We have time for one short question. Very short. Okay.
Thanks for the presentation, and I also appreciate all the videos that you made, so that's really helpful. I have a question about the standard or format of your workflow. Is there any specification that users should follow in order for these Jupyter cells to turn into such a component? And if not, or if so, how does it relate to like a standard, like common workflow language, for example, which it does try to do that?
So there's two elements to answer your question. The first one is that the users never have to worry about the format of the cell because we abstract all the nasty business from them. They just select a cell in a notebook, and we will analyze, figure out what we need to handle for the input and the output, generate a wrapper script, generate the container, and build all that for them. Internally, right now, we use the format for the Argo workflow, but we are also investigating supporting CWL.
Thank you again, Gabriel. And now I'm happy to welcome Kaori Otsu, who will talk to us about VRE as an open scientific gateway to connect EOSC user and resource environments.
Good afternoon. Thank you for joining us until the end of the session, of the day. So, okay, so that's good. So hopefully the slide is gonna look okay because it's PDF format. I'm Kaori Otsu from CREAF. It's a research center. I'm a researcher from CREAF and based in Barcelona. And together with Diego Scardacci, he's from EGI Foundation. We are in this EOSC Focus project. And then today I'm going to talk about just a small part of our task in this project. So this is about the VRE as an open scientific gateway to connect to EOSC user and resource environments. So it was a nice introduction from LifeWatch. And then I would like to talk to Gabriel, maybe later about this environmental domain. Okay. So I saw some of the EOSC dedicated sessions this morning, so I don't really need to talk so much about what EOSC is, but I'm going to focus on this EOSC EU node now that are in public procurement. So in the middle, the EOSC core, the services and procurement, and then data federated, and then other exchange services and more horizontal services. And then it's gonna expand more from the core services. And the third point, the implementation by infra EOSC projects. This is actually key to this project presentation because some of the services, including core services, are actually contributed, implemented by Horizon 2020, and then currently Horizon Europe program. So, okay, so yeah, EOSC Focus project. So this is the project that I'm gonna talk about. 9 organizations in this consortium. And it's a coordination and support action. I already started 2 years ago, and then it's gonna last until next year. And there are many objectives in this project, but then you see, hopefully you can see the work package text, and then work package 3, Syria update and technical development. So that's why I just listed the key objectives of this work package 3. And one of them is to provide an effective stakeholder forum. Now it's called EOSC Forum. And I wouldn't know if it's already effective or not. And then hopefully we have more stakeholders, and it's increasing. And then identify gaps to inform future integrations of the strategic research and innovation agenda. That's Syria. And then last one is, this is a key for us to coordinate infra EOSC projects. It's enabling and an operational, open and fair EOSC ecosystem. So under the Horizon project. So in this work package, we're pretty much focusing on this Horizon Europe projects. Okay. So, okay, hopefully it's readable. So yeah, collaboration among these projects has evolved starting from 2023 January. So we had this EOSC Forum Horizon Europe Technology Group. So technical coordinators were invited to join this group online, and monthly meetings. And then slowly we started to talk what we could do in this forum. And annually, the European Commission hosts this in-person coordination meeting. Then idea of a winter school was born in Brussels. Then September, we actually discussed, okay, so what the opportunity areas are for collaboration. And that was in Madrid. So we actually split into different small groups and interest groups. And then like with some steps to organize and plan, then finally in January this year in Thessaloniki, I don't know anybody from the RAISE project, but that they hosted this winter school. And then, yeah, we had some objectives and roadmaps for short term and a midterm and long term, what we could do within these opportunity areas. And this year again, annual meeting with the commission. And then they decided, we all decided to make this expert group for opportunity areas outside the EOSC project. So now we are going to have towards EOSC Symposium Berlin. I'm going to talk about this a bit later, just a quick, not really quick, but it was a timeline. So yeah, there are 6 opportunity areas starting from PIDs and metadata, more semantic interpretability, and then fair assessment. And then the 4th one, I'm going to focus on user and resource environments. And the graph, I know you're not going to see all the text, but I just wanted to show from the left, and then the 6 opportunity areas, and then different columns that actually show the different projects. So depends on the opportunity area, you can see more projects are participating, or the variety of the projects is seen. Actually, this is in the deliverable of our project, if you like to see more. So yeah, so of course, VRE, we are going to talk about scientific workflow. I just picked up some existing EGI services. So now there is a data hub, and then EGI check-in, and then infrastructure manager, you see all the workflow, and then you can use notebook to analyze and preserve and for storage, and then store and share, replay, the workflow replay, and to be reusable. And yeah, so that's why I put a fair in a fair way. So it has to be findable and accessible, interpretable, and reusable. So, during the winter school, we identified that this is one of the key concepts of EOSC. So we try to address many of the challenges and within this evolving EOSC ecosystem, focusing on VREs that can act as an open scientific gateway and connect EOSC users and communities. And also we try to cover tools and services to facilitate data transfers and discovery and access, and also orchestrate the heterogeneous IT infrastructures. The main objectives are to provide support to harmonize the progress of the systems and VRE services, and mainly to address bigger challenges among the use cases, EOSC use cases, and then highlighting the adoption of EGI resources already in many projects, EOSC projects. And then, so this workshop was really supported by the EGI and Galaxy initiatives. And then in the first row, thank you. And then, of course, EOSC Association Task Force. And I think we were able to establish some hands-on interest groups and to find some common problems and the solutions, possible solutions, and then we're going to work together towards future. So participating projects and then are listed there. So this is actually, interesting enough, that Sebastian and Bjorn in the first row, they collaborated to have this exercise for the participants, and this is from the Euroscience Gateway project. And so using this EGI resources, and then you get the credentials, and then you register and access, but in the Galaxy, and import data, and into the galaxy, and then using so Fairies and Accra Infra, they are the actual project, so they wanted to have their tools, the specific tools. Okay. So then those tools can be run on the Galaxy server. And but then EGI has this infrastructure manager, can host this Pulsar servers. And all the integrated steps are listed here. But probably the next presentation might talk more details about this. So yeah, these are the roadmap. I don't have time to go through everything. So maybe something completed. I can talk about this, increasing user communities. Congratulations to Galaxy and 100,000 users. EGI check-in integration with the Galaxy and all these things. Well, by the way, it's in the deliverable, sorry. It's in the Zenodo, it's published. So so now Galaxy subdomains, Aqua Infra has, within the Galaxy instance, there are subdomains by Aqua Infra Fairies, just an example. So other project collaborations, I already talked about the first 2 or 3. So IOSC Cancer, and then Euroscience Gateway working together to establish trusted VREs. That's another topic that was challenging, that was identified as one of the challenges. But there's another project, Entrust, for example. So they're going to work together about that. And then joint training network with the skills for EOSC and Raise an AI for EOSC. They are working with the Raise synthetic data so that it can be downloaded and analyzed in the AI for EOSC platform. So so just the Galaxy news, they often post collaboration news with EGI. So I just picked them up. And then just recently I joined this webinar on Data Hub and with the OneNode. So I think, some of you might have seen this. Yes, so maybe I don't have time, right? So well, just in maybe the most important part, because this morning that DG Connect, Peter from DG Connect, to talk about this the system of systems. So we know that Jupyter Notebook is going to be used as the application services, and then so we would like to see more that how EGI is going to contribute to one of the nodes and a Galaxy, how it's going to fit in, and all these things. I think I would like to get some more feedback, and then we can discuss and during the symposium in Berlin coming up in 2 weeks or 3 weeks. And so we still have open call for opportunity areas. So, and then into Winter School in January. And I just wanted to say all these events, EOSC Symposium or Winter School, we're going to focus on this EOSC Federation and then EOSC nodes. So more discussion and more collaborations would be great. Thanks so much.
Thank you very much, Kaori. I'm really sorry for the time slots. They're quite short. So if there's no burning question, I suggest we move on to the last speaker. Is that okay? Burning questions? Okay. So I'm very happy to welcome Sebastián Luna Valero, who will continue with the Euroscience Gateway project. Thank you, and let's hope we'll have the presentation. Okay.
There we go. Thank you very much. So actually, I wasn't expecting that, but the previous presentation is a very nice introduction to mine. So I'm going to speak about the Euroscience Gateway project. Briefly, I'll present the project and what we've been doing so far. Like, for example, adding new logging options to the Euroscience Gateway, how to connect it with external computing resources, how to connect it with external storage resources, and a little bit of the work that we've been doing now about job scheduling across Europe. So a little bit of motivation for the Euroscience Gateway. So in Europe, you know, every country or institution is trying to provision infrastructures for science, but normally it's expected that they end up with different hardware configurations, software stack, authentication organization system. So one of the aims of the project is to basically simplify access to all these infrastructures from a unified single entry point, which is the Euroscience Gateway. So at the core of the project, there is the Galaxy platform. And in the end, what the end user needs to access the gateway is a web browser. Once it's in, they have many options like uploading data to the platform, downloading data. There are like over 10,000 tools already installed. That's one of the beauties. If a user asks for tool A and it's installed, when second user comes along later, the user is already available for him as well, or for her. So it's a great way of simplifying the installation of new things, making them available for scientists to do science. They can also create workflows, shared workflows, actually following FAIR principles with FAIR digital objects and integration with AeroCrate. And per analysis, they can save their history with the steps needed from getting the data, processing the data, and visualizing the results. And they can also share the history with others and so on. So, by the way, once they get here, they simply don't know the underlying details of the hardware or the software. They just click buttons and run things, and it's much more simple for them to actually perform science, right? So that's the main advantage. How the project is organized. So at the bottom, you see the infrastructure, cloud, and HPC. HPC normally tends to have their own custom guides for access and use. But then for clouds, the project has been providing infrastructure as code, recipes for automatic deployment of the stack that's required to connect Galaxy here at the core with external computing resources. This is done through the middleware called Pulsar. I'll briefly discuss this later. But also in the project, Arc came along as an additional middleware to also allow Galaxy to talk to external computing resources. And as I mentioned earlier, Galaxy is able to basically export, import workflows from Workflow Hub, talk to Zenodo to archive data, import data, software, everything you can imagine. So I'll move on because we are short of time. This is the list of partners in the project. And then regarding options, the work done at the moment, it's been regarding the integration of 2 new identity providers for Euroscience Gateway. The first one is the WSEG Identity and Access Management, and this is done thanks to the Python social auth plugin. So a Galaxy admin can easily enable access through that IDP. Mainly, this is now used to get an access token to access or send jobs to an ARC site. But the same is possible with EGI check-in also as an identity provider. And again, once you get your access token from EGI check-in, you have access to the whole EGI ecosystem of services. But also there is work to allow the submission of jobs to ARC sites with EGI check-in access tokens. Again, the idea here is that you don't have to create a new account. You just reuse your existing ones either from your academic institutions or for from social media services. So that's about adding new logging options to Euroscience Gateway, but now I'll be discussing how to connect to external storage and external compute. So about external storage, you see on the map, partners of the project have been deploying 6 instances of Galaxy. All of them bring them all to TRL 9 maturity, right? So to make it compelling for scientists. But on top of that, in light blue, perhaps you cannot see it properly, but light blue countries are also participating, adding external computing resources with Pulsar. and Arc. So that's the goal, connecting that to externally available resources. So a little bit more on detail. This is how it looks like underneath it. So the big box is the reference architecture from the Galaxy instance deployed at Freiburg, and they are hosting the main Galaxy instance in Europe. You see Galaxy here in the middle, which is basically talking to a PostgreSQL database and RabbitMQ service. They have NFS shared storage sitting on top of an OpenStack cloud with HT Condor and BMFS for software distribution of container images and even also data distribution. So the way that external sites offer computing resources to Galaxy is that they also use these infrastructure as code recipes to deploy the software stack on top of OpenStack, for example, with HT Condor, BMFS as well, and then Pulsar sitting in between. And this Pulsar middleware is the one connecting to Galaxy through RabbitMQ and say, hey, do you have jobs for me? Send it to me. I'm going to execute them and send you back the results. So with this, now how can a user bring their own compute to Galaxy? So say that I have access to a Galaxy instance, but I also have access to a cloud, for example, the EGI cloud. So using Infrastructure Manager, which is a website to deploy virtual infrastructure with a click of a button, you can say, hey, deploy Pulsar for me. So just click deploy Pulsar. And I have a demo, but no time for the demo. So you can get the slides later and have a look at the demo. Basically, once you are done, you get your Pulsar endpoint. So you go back to Galaxy and say, okay, this is the credentials to access the RabbitMQ. This is the available resources from my Pulsar endpoint. And Galaxy can now talk to Pulsar. And on the right, you see an example, a list of the Pulsar endpoints that are currently available in Galaxy Europe, meaning that if you go there and select one of the Pulsar endpoint, all your jobs are going to be sent across to this Pulsar endpoint. With Arc, there are two options. Either you have access to a managed Arc site, and then you have to talk to the admins if they are able to give you access with one of these access tokens we mentioned earlier. So if they configure Arc to allow access tokens from WLCG or check-in, then in your Galaxy account, you just need to point Galaxy to the remote resource URL from Arc to basically be able to connect to Arc and send jobs there. If not, if you have access to the cloud again, instead of deploying Pulsar, you can deploy Arc. Pulsar is deployed with HT Condor. Arc is deployed with Slurm, so your preferred choice. So that's about bringing your own compute, about bringing your own storage. Basically, here we assume if you have access to object storage in the cloud with one of the famous available options, Azure, AWS, or Google, then you can basically go to Galaxy and enter the details of the name of the bucket, access key, secret key, etc. And Galaxy is then going to be able to use that as a storage backend. If you are using an S3 compatible storage, then you also need to provide the URL to the API endpoint. And then once you do it, you get the list of your connected object storage in Galaxy. And then you can configure in Galaxy, okay, I want to store in that object store, I want to store only the history, or I want to run store only the resource of a tool or of a workflow, or everything. So basically there is granularity to select at which point you want to use the object storage for. In case you have access to the EGI cloud again, there is also a recipe with Infrastructure Manager to deploy MinIO on top of the cloud. And again, you get your S3 endpoint and you can plug that into Galaxy. In addition to cloud storage, thanks to the work in the project, Galaxy is now also able to talk to EGI Data Hub, which is based on the One Data technology. In this example, Galaxy is able to basically connect to One Data to, for example, provision all the training for the Galaxy training network. So someone repeating one of the tutorials in the GTN, they can basically go to Galaxy, all the data is there, they can easily replicate it and import the data from this publicly accessible space in One Data. The other option is if you have access to a space in One Data, you can configure it as a file source plugin, as a file source for Galaxy, meaning that you can import and export datasets between Galaxy and One Data. And coming soon is the integration with One Data as an object store, as we mentioned earlier, but this time with One Data. And again, you have this form to fill up all the details about how to access the One Data object store. Finally, job scheduling. Okay, so we have this scenario with your Galaxy instance connected to external resources, compute or storage. How can we efficiently schedule jobs properly in this scenario? So a bit of brainstorming in Zoom, you know, there are time to discuss. This is one of the results, but more formally, yeah, okay. So we decided let's reuse this InfluxDB instance already available in the Galaxy central instance. So Pulsar and Galaxy can dump usage information to say how busy or how empty they are, or even more interesting, for example, per tool, how long does it take to run a tool? What are the waiting times? What's the execution time? So everything is dumped into the InfluxDB. Then there is a TPB module in Galaxy doing kind of a pre-filtering of out of all the destinations available to compute jobs, what are the kind of the candidate ones to run those jobs? And that's basically a matchmaking of the number of CPU cores that you need and the number of CPU available in the destination. So, but this is based on static information. So that's now enriched with the dynamic information we are dumping from Galaxy and Pulsar. And basically, the project has been working on a standalone API endpoint to do the meta scheduling, getting the pre-filter sites from TPB, the dynamic information from InfluxDB. And another cool thing in the project is this usage information is being used also to visualize how busy is the Pulsar network and the Galaxy instances. I'll show you a little bit more about that later. But basically, with this new central API endpoint, there is a matchmaking between, we're collecting about the sites, current and historical data, like how busy they are and the time it takes to run things. Also, we are taking into account the data locality of the data sets. So in the end, it's a simple weighting of send the job to the closest site where the data is. So you don't have to move the data around a lot. Or perhaps send the job to the place that is more empty at the moment, has more space for computing new tasks. But there is work in progress to improve this simple weighting with more advanced meta scheduling algorithms. This is something that we are focusing right now and will be the focus until the end of the project. And you see a snippet here on how it works. There is also a Swagger UI here if you want to play around with the API endpoint as well. And finally, you see here, this is again a prototype, but the idea is that every circle here represents either a Galaxy instance or a Pulsar endpoint. And in the circle, you see in green the running jobs, in yellow the waiting, and in red the ones hold on in the queue. So thanks to everybody, especially to these people from the Euroscience Gateway project. That's everything. Thank you.
Thank you very much, Sebastian. Do you have questions for Sebastian? Who went very, very, very fast to give the time. Okay, when?
How easy would it be to add more portals accessible to this kind of network? So is it something easy to add new portals providing resources or workflows, or how
Yeah,
How would
we
it
have
be?
the team here. It's all in the project. There's also been work updating documentation and recipes to make the deployment of Galaxy easier. So everything is open source upstream. You just need to get the documentation, the code, and try it yourself. There is great support also from the team if you run into problems. So, but yeah, it's very easy, and there are in the project only it's 6 main instances deployed, but other people outside of the project are also contacting the team to deploy new instances. So it's very easy. Now running that into production with many users as they do, that's a different story. Like I mean, it's yeah, the project I think is now over 100K users registered in the main Galaxy instance, and yeah, that's a challenge, but due to the size, not to the complexity of the deployment.
Okay, thank you very much. Normally we had 5 minutes of questions at the end for all speakers. We're a bit late on time, but this is the last session. So I don't know if you have the time, the patience to ask 1 or 2 more questions, maybe also to the speakers to whom we didn't have the time to ask questions during the session. If not, I encourage you to go and see them and discuss directly with them. So let's thank all the speakers again. Thank you very much. So questions will be later at the dinner or tomorrow during the day. Thank you and have a nice evening. See you.